Okay, thank you very much. Good morning. Thank you for being here in this seminar today on Monday. We have the great honor to receive Florian Seitz from the University of Basel. He's going to talk to us about his work. So thank you very much for being here, Florian. And let me introduce our guest today with a little review of his career. And also, I need to tell you about the instructions of today's session. As you know, you have your microphone off, but if you want to ask some question, or maybe you can leave it in the chat, and also you can raise your hand and we can take your question. I can ability your microphone. So today we have the great honor to receive Florian Ismael Seitz today in this seminar. So let me talk to you about him a little bit. He obtained his Bachelor of Science in Psychology from the University of Basel with the thesis title, Can Inclusive Fitness Theory Predict Discriminative Grandparental Solicitude? Supervised by Dr. Jenna Jarecki and Dr. Jörg Riebskamp. A review of evolutionary theories of grandparental investment and discussion of an own hypothesis explaining discriminative grandparental solicitude with information accumulation. He obtained his Master of Science in Psychology from the University of Basel with a specialization in social, economic, and decision psychology, with his thesis on the discrete metric in categorization under time pressure. And now he's a student, a PhD student in psychology at the University of Basel with his thesis of new approaches to cognition, developing and testing multifaceted view on similarity. And for me, it's a great honor to receive him. Florian, thank you very much for this great opportunity. The stage is all yours. Welcome.
Thanks a lot for the kind introduction. I'm going to share my screen to begin. Okay. If anything shouldn't be visible to you, please tell me.
Yes, perfect, Florian. Everything is great.
Okay. So hello, everyone. My name is Florian Seitz. I'm from the University of Basel in Switzerland, and I'm going to present to you cognitive models and our package for formal cognitive modeling. The Cognitive Models package is joint work of Jana Jarecki and myself. And there is an ICCM paper on the package available under the link presented above. So feel free to check it out, to read it. I'm also happy to send it around if you're interested. Now to start, why should we do a cognitive modeling package? On the one hand, there has been a recent call for formalizing psychological theories, and cognitive modeling is one way of doing so. The argument is that formalized psychological theories, and thus cognitive models, make hypotheses testable, falsifiable, and ultimately aid in theory development and scientific progress. So it is argued that cognitive modeling is an important step to make further scientific progresses in psychology. On the other hand, many cognitive models share a common ground. So for instance, you will potentially want to fit any cognitive model to human data, estimate parameters, and then use these estimated parameters to predict responses, to predict data. A package is one way of exploiting this common ground between different cognitive models. Furthermore, cognitive modeling should be transparent, trusted, and robust. And these criteria impose several coding constraints, such as, for instance, code reproducibility by a third party, meaning that someone else can re-obtain your results by reproducing your code. Another aspect is code reusability. So code should be easy to use, easy to understand, and easy to modify. Now, all these aspects can, in our view, can be optimally exploited using a standardized package for cognitive modeling. And this is exactly what we aim to do with our software package Cognitivemodels. So Cognitivemodels is a free tool for formal cognitive modeling in the free software program R. And it gives access to a range of cognitive models from multiple domains in one single library. And there are three main advantages of the package. So first, its efficiency. The package uses a standardized syntax across cognitive models. And this syntax is similar to the syntax of ANOVA and regression commands. So people or modelers familiar to common R commands will also very quickly accommodate to the syntax of the Cognitivemodels package. Furthermore, the package has a series of common methods for all models, exploiting this common ground I was talking about before, the common ground between the different cognitive models. A second advantage of the package is the robustness of its code. The package implements unit tests of modeling functions. So for instance, the package tests if parameters which have been published in studies can be re-estimated with the same data, with the same underlying data. And it also checks if, given a set of parameter values, model predictions are correct, if they are accurate, if they are correct. Furthermore, it is possible to, for every user of the package, to report bugs via GitHub. A third advantage is the flexibility of the package. On the one hand, you can adjust the package to your own individual needs. So for instance, you can make parameter constraints. We will look at this in detail afterwards. And as a second, on the other hand, there is a general purpose model development backend, which allows experienced modelers to add further cognitive models to the package. And these further cognitive models would then have the same methods as all the other models. I'm not going to talk about this model development backend today. I'm going to concentrate on the other points. Now, in the following, I'm going to show you all the models that are present in the Cognitivemodels package. You see the different models in the rows. There is, for instance, the generalized context model, categorization model. There is also a model for decisions under risk, such as cumulative prospect theory. Or there is, for instance, a Bayesian learning model. And each model has its own function call within the Cognitivemodels package. And what you're seeing now in the remaining columns are the arguments needed for the different functions. And what you're seeing is that every function call needs the same 4 basic arguments. And this is what I was talking about with the common syntax, the standardized syntax. So, irrespective of which model you want to run, you need the same 4 basic arguments. You need to specify a formula. The left-hand side of the formula contains the variable, the output variable, so the human responses. Whereas the right-hand side of the formula contains the different input variables. The different input variables within a stimulus are separated from each other via the plus sign. And if within a trial you see multiple stimuli, such as, for instance, if you choose 1 gamble out of 2, and you want to model this with the cumulative prospect theory, the different gambles will be separated from each other via the vertical dash via this pipe. So the plus sign separates variable for within stimuli, and the dash, the vertical dash separates the variables between stimuli within the same trial. In the second argument, in the data argument, you just need to specify which data which object contains the variables used in the formula argument. In the first fixed argument, you can specify optional parameter constraints if you want to. I'm not going to talk about this into detail now, as we will look at this into very close detail in the following. Finally, there is a fourth argument, a choice rule argument, which is sometimes optional, sometimes mandatory. And the choice rule argument is basically a linking function between the continuous model predictions and discrete participant responses. In the following, I'm going to show you the syntax of the Cognitive Models package with examples using the generalized context model. Now, the generalized context model is a formal model of categorization, and it assumes that similarity to previously experienced category members determines the categorization of a new object. The basic intuition is that the object belongs most likely to the category to whose members it is most similar. Formally, the model assumes that the probability of assigning an object I to category J is given by the similarity of the object I to all members of category J divided by the similarity to all members of all categories. The formula contains one parameter which denotes a bias, a tendency towards responding with a certain category. So for instance, Bj is the bias towards category J. The higher Bj is, the more you are inclined with responding with category J, irrespective of the stimulus you're seeing at the moment. The different bias parameters are constrained to sum up to 1 in total, and all have to lie within the range 0 and 1. The generalized context model computes the similarity between two objects I and J based on their Minkowski distance. And the Minkowski distance can be interpreted as the summed differences between the two objects across their features, across the features that constitute these objects. Formally, this is given with the following function. What you're seeing in the middle of the function is that the two objects I and J are compared with each other. So differences are computed between the feature values of object I and J across features M. And this is summed up across features M. And also this function as well contains a series of parameters. So there is the relative attention for each feature M. And these attention weights, omega, they're constrained also to sum up to 1, and each weight has to lie within the range of 0 and 1. There is the norm of the distance function, which typically takes the value 1 or 2. There is Q, the relation between distance and psychological similarity. And finally, there is lambda, the sensitivity parameter towards small distances. Basically, the higher lambda is, the more sharply psychological similarity declines with increasing distance, with increasing differences between the objects. I'm going to, in the following, apply the generalized context model to categorization learning data from Nosovsky, from a study of Nosovsky of the year 1989. And in this study, people had to classify lines of varying lengths and varying angles into two categories. People had to classify 16 of these stimuli, as you're seeing here, in 4 different conditions. Now, I'm going to focus on the size condition, in which people had to learn. In the first phase, they had to learn to classify with feedback 7 stimuli, 4 from category 1 and 3 from category 2. And in the second phase, after being able to accurately classify these 7 stimuli, people classified all 16 stimuli. And what I'm going to do now is I'm going to switch to R Studio, and I'm going to walk through the code with which we can analyze this data using the cognitive models package one by one. Just as a small detail, at the beginning of you need, of course, to install the package, and you can do this using the install GitHub command and then library cognitive models. And what is necessary if you want to use this model, it is necessary to have the RCPP package and to have the latest version of the MATLAB package. So if you want to use the cognitive models package, be sure to install the latest versions of the MATLAB package and to install the RCPP package. Let's begin. Let us look at the data, which is the data from the Nosovsky experiment. This data is available within the package and can be called using the function data. The following lines of code only take the size condition of this whole experiment and only look at the learning at the first phase of the experiment. So the trials where people received feedback for their categorization. And as you see here in this data set, each row represents one trial. So people see a specific line of with a specific angle and specific size, respond with a certain response, so here with 0, and then receive feedback about the true category. Then the next trial follows with a new stimulus. People respond to it and again receive information about the true category of the stimulus. Now, if you want to model this data, we have to use the GCM function in the cognitive models package. Now, to implement the GCM with the package, recall that you need those 4 basic arguments, the formula argument. Oh, okay. You need 4 basic arguments. You need the formula argument, the data argument. You could have the fixed argument, but it's where you specify your parameter constraints, which are not specified here because we don't want to specify any parameter constraints for the beginning. And you need to specify the choice rule. For the GCM, not using a choice rule is the default, so we would not need to specify this a priori, because none is the default. But I've done it here, so you see the argument. The GCM has one further argument, which is important, the class argument, which contains the variable with the true category of the stimuli. So the true category variable, as you see here on the right in this data frame. Now these lines of code are enough to fit the GCM to this data. When I run this, you will see in red that the model is fitting its 3 parameters. The 3 parameters we discussed about the 3 parameters of the GCM we discussed before. So there's, for instance, lambda, R, Q, the bias parameter for category 0, and then here you see the parameter for angle, and this is nothing else than the attention weight for the variable angle, for the feature angle. So how much relative attention you put to the angle of the line. You also see here and that the model fits the three parameters by maximizing log likelihood, a binomial probability density function, using the SolNP solver in R. These are basic, or these are default settings, and we will look at how to change them afterwards. So I've already fitted all the models I'm going to show you today beforehand, so I can stop this here and I can directly show you the model. So what is displayed after fitting the model. You can just look at the model by executing the model, and you will see the fitted values for the different three parameters. So you have here the three parameter estimates, and you have two constrained and fixed parameters, the attention weight for size and the attention weight for the bias, the category bias for the second category. They are constrained because, as we've seen before, the attention weights need to sum up to 1. So angle and size needs to sum up to 1. And the bias for both category needs also to sum up to 1. And that's why the second one of both parameters is constrained. You can get a very similar picture by executing coefficients of the model. Here you see just basically all fitted coefficients of all parameters. A further potential thing you can do is make a summary directly of the model, which also shows you the parameter estimates, but furthermore also shows you already some basic fit measures, such as log likelihood or mean squared error, Akaiki's information criterion and Bayesian information criterion. Now, as I've told you before, the model, the GCM, already has some parameter constraints implemented a priori. Attention weights need to sum up to 1, and category biases also need to sum up to 1. And you can look at these parameter constraints by executing the command constraints. And you see here, angle and size need to sum up to 1, and the two category biases as well. We can add further parameter constraints if we want to the model. For instance, we could say we want to fix the parameters R and Q to specific values, for instance, to the values 1. We do this by adding the argument fix, which I've told you before. The argument fix is a named list containing all the parameters you want to fix and the corresponding values. So here in this chunk of code, we're fitting a generalized context model which has fixed parameter values for R and Q equal to 1 each. And we can see that this worked by, again, executing the model after we fitted it. And we see now R and Q appear now in the range of the constrained and or fixed parameters with a value of 1. And these implemented constraints are also visible when we use the constraints method. You see here, R is equal to 1 and Q is equal to 1 as well. We can, of course, use different values, such as the value 2 for R and Q. This doesn't change anything. This is just another value for the same parameters. It also fits a generalized context model with fixed parameters for R and Q. As you see here, R is equal to 2, Q is equal to 2. We can not only fix parameters to specific values, we can also set up equality constraints with the cognitive models package. Equality constraints mean that two parameters need to have the same value. So in this third model, you see that R needs to be equal to Q. And what is being done here is that the model fits a value for the parameter of Q and automatically sets the value of the parameter R to the same value as for parameter Q. You see this here. We have this one additional linear constraint saying that R minus Q must be equal to 0 or R must be equal to Q. Now, of course, we can also combine fixing constraints and equality constraints, such as in the fourth model, where we specify that Q is equal to 2 and R needs to be equal to Q. And this is basically exactly the same as if we would list Q is equal to 2 and R is equal to 2. Just with another logic of parameter constraints behind it, as you see in the constraints as well. And of course, this model now here, this fourth model, is exactly the same model as our second model, where we use the fixing constraints, where we fix Q to 2 and R to 2. And to show you that this is the exactly same model that is being fit, we can compare the coefficients for the model 2, the parameter estimates for model 2, with the parameter estimates for model 4. And we see for all of the parameters, the estimates are exactly the same. Now, after fitting the model we wanted to fit, we can look at the goodness of fit of this model. Within the Cognitive Models package, we can calculate a series of goodness of fit measures and also make model comparisons. So one thing we can do is we can calculate, for instance, log likelihood of the model. You can also calculate BIC criterion, the AIC criterion, and we can also print an error summary table with the ANOVA method, with the sum of squares and the mean of squares. If we use the ANOVA method on more than one model, we can further make a model comparison. Here, for instance, we compare model 1 and model 2 with a chi-squared test to test which of the two models better fits the data, for instance. For instance, if we compare model 2 and model 4, which are logically exactly the same models, we see they have exactly the same values as a chi-squared value of 0, meaning they are the same model, basically. We can even compare more than two models with each other. For instance, here we can compare 4 models with each other, and each model is compared with the precedent model here in this ANOVA result. So model 2 is compared with model 1, model 3 is compared with model 2, and model 4 is compared with model 3. And what we see in here basically is that model 3 gives a better fit than model 2, but model 4 cannot further improve the fit of the model to the data. So model 3 seems to be here kind of the best models which we looked at till now. Now, furthermore, we can use every function or every model, every cognitive model in the Cognitive Models package can be used to make model predictions with the predict method. By executing predict model 4, we predict GCM categorization probabilities for all the trials in our data. So this is now one huge vector, and one value is one trial, basically, the categorization probability for one trial. We cannot only predict responses or response probabilities for the data underlying the the model, we can also predict response probabilities for new data. To do this, we use the optional argument new data. And here we specify, for instance, we want to predict the data which from the second phase of this category learning experiment where people didn't receive feedback anymore. So this also gives us a vector of categorization probabilities, response probabilities. Now what I'm doing here is I'm executing in this following two lines, I'm executing exactly the same code, and I'm storing the predictions as a variable in our data set. But as you see here, next to the response, we now have a further variable containing the model predictions, given the fitted model, given the parameter estimates. And this is, of course, very handy because now we can use these predictions to look at how well do they match, for instance, the responses of participants. So just as to give one very brief example, we can look at all stimuli which people did not experience in the first phase of the experiment. And we can look at, for instance, how far or how close does the prediction approximate the mean response for each of these stimuli. This would be just one thing you could do now with these predictions. Now, these are the basic tools which you can do with the Cognitive Models package. There are some advanced modeling options which you can do, and I want to briefly introduce you to them. The first one would be setting a choice rule. For the GCM, the default choice rule is none, so that you don't use a choice rule. However, you could use, for instance, the softmax choice rule, or any choice rule basically which maps continuous response predictions to discrete responses. So here in this GCM model, we use, for instance, the softmax choice rule, and also have a set of parameter constraints. Next to setting a choice rule, we can also change the lower and upper bounds of our free parameters. So if we look here at the part space, parameter space of the generalized complex model, we see for different parameters, x1 and x2 are denote the two attention weights, so angle and size. We see the lower boundaries of these parameter values and the upper boundaries of these parameter values. For instance, we see that both attention weights need to lie within 0 and 1. The same is holding for the category bias parameters. And we also see during model fitting with which parameter values the solver, the optimization solver starts. And what we can do now is we can change these lower and upper bounds of the free parameters, as we do here in model 6. For instance, we changed the parameter space or the parameter range for the parameter lambda from 0 to 10 to ranging from 0 to 20. So the lower boundary LB is 0 and the upper boundary is 20. A third thing we can do is we can change the goodness of fit measure used during model fitting. Remember that the default is log likelihood. For our categorization data, a binary probability density function. But we could also choose, for instance, to use the mean squared error as the fit measure. And we also do this with the same argument options, where we specify that the fit measure should be MSE. So for all these advanced modeling options, we use the argument options, and we specify, for instance, the lower boundary, the upper boundary, or the fit measure. Now here I'm just showing you one model combining all we learned so far, what we can do with the cognitive models package. So for instance, here we applied a series of constraints, 2 fixing constraints, 1 equality constraint. We set the choice rule to the softmax choice rule. And we changed the lower and upper boundaries of lambda again to 0 and 20. And we changed the fit measure, for instance, to the mean squared error. So we see here in this model that we use only a few lines of code to make a model that is extremely accustomed, or that is extremely tailored to our own individual needs. Now, what I'm going to show you in the next step is what I've been talking to you at the beginning of my talk, that the code underlying the cognitive models package is robust. What I'm going to show you is what kind of unit tests we have implemented in this package to assure that the code is correct and accurate. And I'm going to again show you this with the data from Nosowski 98, this time just in an aggregated version. It's the same data, just aggregated, because Nosowski has made some of his analyses are done on this aggregated data. So what you see here are the different stimuli in the rows, again with the feature values, how often this stimulus has been experienced, how often it has been classified as category 1, and the corresponding percentage of category 1 classifications. So P ops is just ops cat divided by n. And now what I'm going to do in this next model is I'm going to fit the GCM in exactly the same way as Nosowski has done it in his analysis. And what I'm hoping at the end is that I can recover the coefficients he received in his own model fitting. So the target coefficients here are the coefficients Nosowski reported in his paper. And what I'm going to look at is if the parameters of our model, which you can look at with this par method here, if these parameters match the target coefficients. I've rounded the parameters to 2 values after the comma. And as we see here in the following, every parameter estimate is exactly the same as the parameter estimates of Nosowski. We can go even one step further and look at if we can reproduce the response predictions of Nosowski reported in his paper. So this vector shows us the response predictions for all 16 stimuli given the fitted parameters. And what we do here is now given our fitted model, we predict also the response probabilities for every stimulus. And to check if all predictions line, and we see this is the case. One last unit test to show you is that, since Nosowski reported his DSSE of the model, and we can show you that our model can reproduce this goodness of fit measure. And these 3 unit tests you're seeing, we have now seen in these last lines, these are the kind of unit tests we have implemented and which are ran automatically within the package to ensure that the package produces accurate and correct parameter estimates and model predictions. I'm seeing that I'm already quite so that my talk time is already quite over. It's 6:45. At my time, it's 6:45. I guess in your time, it's 1:45 to noon. We have two options basically. What I can go on with by showing you some more features with the cumulative prospect theory, or if you want, we can also already now start a discussion and discuss what we have seen so far. I'm open to both, basically.
Yes, Florian, I think that it could be great if you can explain us more around it. Maybe we can start a discussion. I think that the prospect theory will be very nice, but I think that we can lend some ideas for our students and maybe to talk about the consequences of this. Maybe if we can start some discussion, Florian, if it's okay for you.
Perfect.
Yes, so if anybody has a question, I have a couple of questions, Florian, that I'm very interested because, as I mentioned before, most of my students that are connected today, we already passed this chapter of the course, that is the categorization part. So we saw the example that Jerome Busmeyer and Adele put in their book about the X-rays, that you have these X-rays and you have two dimensions, the diameter and the luminosity of the node, and you need to categorize if it's category A or is category B. So we use the idea of Nosovsky of having these dimensions in a prototype model and an exemplar model. So one of my questions is, you have several parameters that you move, as for example, the choice rule. And I want to ask you, what does it mean, psychologically speaking, the choice rule that you select from none, from the softmax, or some other rule?
Okay, so the choice rule is basically, so the definition of a choice rule is a mapping function between continuous model predictions and discrete human responses. I'll make one drastic example to make this clear. For instance, if you want to use prospect theory, the resulting output of the model will be an overall value of a gamble, right? But if we only have, and this overall value can range from, I think, from 0 to potentially to infinite, I would say, not 100% sure. But basically, it is not constrained within the range of 1 and 0, for instance. And using a choice rule here can help us now to transform this range of output values of the prospect theory model to the range of response probabilities, for instance. So we could use, for instance, something like Lewis's choice axiom, where you basically what you do there is you would, if you want to know the response if you want to know the probability for choosing gamble A, you would divide the value of this gamble A by the values of all gambles. Okay, so you make basically a share of value. And this transformation, of course, then, or this transforms the output to the range of 0 and 1 and can then predict response probabilities. This is one example. If you don't use a choice rule in this example, you would have values which are not constrained within this range, and it would be difficult to predict choice probabilities, for instance. In the GCM, maybe let's talk about the softmax choice rule, because this is a choice rule which is relatively often implemented in the GCM, as far as I know. The softmax choice rule is basically a function which is able to make the model more or less deterministic. and it has one parameter which is also fitted to the data. And the higher value of this parameter is, the less deterministic the categorization predictions are. In the most extreme cases, the model will result in categorization predictions of 0.50 all the time. So basically random response. And the very low value of this parameter in the softmax choice rule will make categorization predictions very deterministic. So if the resulting categorization probability of the GCM is higher than 0.50, and you have a very low parameter for the softmax choice rule, this will turn the prediction to an almost deterministic response of 1. And so these different choice rules basically, so they can, first of all, they can help us transform data to different scales, and to model more or less deterministic behavior.
Okay, perfect. Another question that I have from your parameters, what is better to select for the metric? The Euclidean one, the city one, because I think that you can also fix that, right? So exactly. Psychologically speaking, which is better, or what metric gives you the best prediction for the models? I don't know if it depends of other things.
Yes, actually, I think it depends on the features which constitute your stimuli. So there is there's quite some work of Nosowski, I think, on this topic. And the basic result is that if you have features which are readily separable from each other, such as, for instance, size and angle, you can, by eye, very well discriminate between these two features, right? In this case, studies have found that setting the value of R to 1, so using a city block distance, is better than the Euclidean distance with R set to 2. However, if you have features which are not readily separable, which are, for instance, if you see colors of different saturation and of different brightness, it is very difficult to discriminate brightness and saturation by eye. And in these cases, studies have found that setting the value to 2, so using a Euclidean distance, provides a better fit to data. So it depends mostly on the stimulus features, exactly.
Okay, great. And finally, if everybody has a question, you can raise your hand also, but I don't want to do all the questions by myself, but I have another question, because we are trying to do some thesis on undergraduate thesis using the, well, for example, your code. But one thing that I would like to ask you is, what can you tell us about the, for example, plotting a result, or showing some of the result? What can you do with this?
So basically, you can use all the output which is generated with the package for plotting stuff. One proposition I would have, like right now, is, for instance, you could plot the predictions your model gave and people's responses against each other, for instance. So remember, there was this one, when I executed the prediction code, I stored these predictions as values or as a variable in our data set. And we could now perfectly use this data set with, for instance, with common R plotting functions, such as the R basic plot or ggplot, and just specify the variables we want to plot. So I think what we need to do in general is that we need to save the output we generate with our models as a variable in a data frame. So for instance, that you expand your data set, which contains the participants' responses, by model predictions. And then you can use this data set for making Bayesian plotting as you would do it with any data set.
Okay. Okay. And finally, I would like to ask you, sorry, I have a lot of questions, but I would like to ask you, Florian, about this part of, I don't know if you can tell us about the consequences of psychological doing models. We know that we can study in a traditional way, doing some tests, and then we apply some instrument, we collect the data, doing some ANOVA, doing some stuff like that. But what happens? Why is important to try to go in this way, doing some modeling and for sure using your package?
So I think cognitive modeling is one great tool to formalize psychological theories and to do computational modeling, to do mathematical modeling, formal modeling. Using formalized or testing formalized theories is, in my opinion, a very important step because it makes hypotheses much more falsifiable than using verbatim models. So if you use only verbatim models, there is always quite a huge space for interpretation left. And so to make, I'll go with one example of Gerd Gigerenzer, who makes this point very clear quite often. So, for instance, Gerd Gigerenzer has already stated or noted the fact that, for instance, in this heuristics and biases research of Kahneman and Tversky, often the biases are on a very informal way, specified in an informal way. And he even said, for instance, that there are two biases which basically state directly the opposite of each other, but they are both considered as biases of human judgments. So this is the hot hand fallacy, which basically says that after experiencing something, your impression that you will re-experience this thing increases. So the probability of getting the same outcome again is basically higher than it should be according to randomness. And then there is the I've forgot the name now. I forgot now the name of the second fallacy, which basically says exactly the opposite. So if you for instance, if you throw a coin and you get tails, you think now it should be heads. It should be turned for heads now, right? So your subjective probability of seeing heads is higher than would be assumed according to the randomness of the coin. And so these two biases basically denote two opposite cognitive processes. And the question that now arises is how is this possible that two biases, which are basically saying the opposite of each other, exist? And by using formal theories, formal models of cognition, we would now be able to exactly specify which cognitive processes are present in each of these two biases, and potentially also be able to explain why can these two biases, which seem to be the contrary of each other, why can they exist, both of them? And so using formalizing theories is basically, it's opening a window to the human mind to say it a bit philosophically, because it makes hypotheses very testable, very falsifiable. We know much more about the cognitive processes underlying a specific behavior, a specific bias. And this is why I think cognitive modeling is a very important tool in psychological research in general.
Okay.
I'm not sure if this answers your question.
Yes. Yes, for sure. And also, I would like to join with the question of Emmanuel in the chat that he says, what need to do for introducing this field? And in that sense, I would like to ask you for your advice for our students that are interested in this area, what they need to do and what they need to know in order to start in this area.
I think so. So it's a quite so as a research area, I think it's a very programming intensive area. So being able to program in R, in Python is certainly very recommended, very useful. And else, I think, I mean, I don't see that there are too many things that you need to be able to do to dive into this field. So as for myself, I can, for instance, talk to myself. I basically stumbled a bit into this field because I was reading a paper about categorization. It's about I think it was the paper of Nosowski. And I found the topic extremely interesting, and I really enjoyed the methodological approach he used, so this cognitive modeling approach he used. And this was basically the first time I've ever heard of cognitive modeling then. And by time I got to know the methodological things, such as what I was talking about today with parameter estimation, model predicting, goodness of fit. I learned about different approaches to modeling, Bayesian modeling. I learned about different theories, different models, what separates the models from each other. So I think to give an advice, I really would say programming is really the most important advice, I would say. And it's also useful even if you don't go into this direction, I would say. Programming is generally very useful. And else, I would just basically start with reading papers of topics which we're really interested in. So if you're interested in modeling decisions under risk, I know that decisions under risk, prospect theory is very popular, and start reading these papers. And I think this is I would give this as advice: just dive into it, because it's the experience basically which I think which is important in this domain. Just to start with it, start modeling, and yeah.
Perfect. Thank you very much, Florian. And I have one last question. What do you do for combined task? For example, the categorization and decision-making task together, that one follows the other. You can do this in your program?
So potentially you would have to run two models after each other. I think this could be possible. I'm not 100% sure how you think of it conceptually. So basically, you would, for instance, have a categorization task where you would have to categorize stimuli into the categories, and then you would choose between these stimuli the one you prefer, something like this.
Yes, this one, for example, the Thousand and James Townsend and all these people work when you have two faces that change in the side of the face and the size of the lips, and then you have to decide, categorize these faces as bad or good faces, and then you have to decide if you need to approach or to withdraw of these faces. So you have these two stages.
So I think you would have to need to run two models after each other sequentially. If the input of the second model depends on the output of the first model, then you would have to run the first model, use this output, save it in your data frame, and then use it as the input variable in the second model. I think this is one thing. Directly combining two models within one call is, as far as I know, not possible. You would have to run it sequentially.
Okay, perfect. That's helps a lot. Thank you very much. So I don't know if anyone has another question, but I think it's very interesting, Florian. I told you on the email, and I told you at the beginning, I think it's very interesting, the thing that you are doing. I think it's an area that most of the people, well, not most, but some people could move and some people could start doing some research. I would like to start also with my students doing this mostly on undergraduate thesis. But I would like to ask you, as a final comment, your final recommendation as starting doing research in this area.
Advice in what sense? How to?
As a motivation or something like, yes, finding the motivation to start in this area.
Find motivation. So the first thing that got into mind is that I really can recommend you to do this kind of research because it's just very interesting. You learn a lot of tools which are very helpful across different research domains. So as I told, programming skills, your mathematical skills get better. I had the impression with my mathematical skills they improved with time. So this is one thing I can. So that's already why I could recommend to do it. And what I really like about cognitive modeling is that it is a very global methodological tool. Basically, you could approach any psychological topic you're interested in using cognitive modeling. You can approach categorization, decisions under risk, judgments. You can approach memory with cognitive modeling. You can approach very practical subjects with this thing. For instance, if you want to, I don't know, if you want to you could model, for instance, also categorization data for natural images. You can model choices between real things. So, for instance, if you want to look at, I don't know, which of two products people would prefer, you can use cognitive model across different domains. You can use it in artificial settings. You can use it in more natural settings. So there's a really wide scope where you can use cognitive modeling, and this is one thing I really like about it. So it doesn't really depend on the topic you like in psychology. Cognitive modeling is, in my opinion, a very fruitful tool for a fruitful approach for any kind of topic you would want to approach.
Perfect. Thank you very much, Florian. And Valeria says, excellent. Thank you for your advice and your interesting presentation. Mitzi, also, thank you very much for your talk. I find this area very interesting, and your work just inspired me to dive into this field.
Very happy about this. Gracias.
Perfect. Thank you very much, Florian.